World is event-based. Countless number of actions, situations, events are happening all around us every millisecond of our lives. It is no different with systems that we all work with. The need to react to these events in real time is crucial these days. Even a few years ago, running some jobs on daily batches of data was just fine, was good enough. However, the world moved on since then. Everyone wants to have an insight almost immediately because any lag may cause opportunity loss for the business. Sometimes it's quite challenging task because the amount of these events can be quite large. Good news is there are few techniques that can help us engineers to build systems that fulfill this requirement of immediate reaction. One of them is stream processing, and we will do a deep dive into this technique today. We will also see some practical examples with Kafka streams in area of risk management systems. My name is Daniel Jagielski. I am working in VirtusLab. Currently, I am managing a team that is working with very similar area to this one, with a platform for one of the biggest online groceries, and we are detecting some malicious users' behavior. So this topic is quite close to my heart. Let's run a bit of warm-up exercise. Who has heard about GDPR, RODO in Polish? Okay. Who hasn't? How did you do that, mate?
Because I work for an American company.
Okay, sure.
I work.
Anyway, annoying forms, different regulations than before. This is what we think about GDPR. But there is some good part about this as well. What we can observe recently, due to all of this GDPR hassle, is that companies tend to invest more in areas of data protection and privacy in general, in security. They think about it more seriously than they used to. That's because 4% of annual income, that is the maximum amount of fine that company can get, can be quite harmful for even the biggest players. Although there are also different motivations for making platforms more secure, like preventing reputation loss and other damages caused by hackers. So let's rewind the time a bit and imagine it's 16th of January 2019. Troy Hunt, who is one of the biggest experts in area of web application security, has released a blog post and a tweet about it with something that he called collection number 1. The collection contains 773 million records with unique customers' credentials, so username passwords, that leaked from different websites across the world. So I would bet that most of us sitting in this room could find their emails in this collection. If you haven't done that yet, please check it after the session. haveibeenpwned.com is the website that can do it for you. Now, let's imagine we are working in a successful organization that exposes some of our services for online customers. What can happen in such situation after this date? This is what happens. Credential stuffing attack. All types of attackers, starting from script kiddies to huge botnet owners, arise. They run their scripts, their applications, and that are just iterating over the collection and try to log in to different online platforms, different platforms that they are targeting. Unfortunately, some even some small part of their attempts is successful, because people, users, do not care about their own security. So they tend to reuse their passwords across internet, across different websites. So no matter how secure your password is in this case, if it leaks from one of your hobby forums that is insecure most probably, your all online identities are at risk. So when you work for such organization, what you can observe is the number of calls to your call center is rising, and people are reporting that their goods were stolen. If you are a noble organization, you want to keep your customers happy, you want to repay them their loss. So in such case, management is probably getting anxious, they want to fight back. This is how the challenge is born. The challenge for your team to increase security level of the platform. So depending on time and money already spent by the company is in security area, the platform may have different shape, different state at the moment you start working on it. So the worst case scenario is it looks like that. So pretty much unsecure. And what management wants is that one. So plenty of steps in between. So what would you start with? You should start analyzing requirements. So after a long meeting with the business, you agree that you should, in the first iteration, you should analyze login attempts. This is something that you would like to start with and then enrich the platform. Your next requirement is to detect attempts from new devices for given user. The same for locations. So you are probably all familiar with the emails coming from Google, Facebook that someone has accessed your account from this location, from this device. This is something that we want to build here. We want to detect attempts that are coming from botnet agents and brute force attacks. So someone is just trying, someone knows the email of some account and trying different password to get into this account, to steal their goods. So this is something that we are interested in as platform owners. Let's now define our input, which is login attempt. We are interested in the result of this login operation, obviously. It may be successful or unsuccessful. We are interested in session identifier, so let's agree now that all consecutive attempts sent from particular user interaction from one tab are coming with the same session identifier. We are also interested in timestamp of this particular attempt, user identifier, so if we were able to match users' input to something in our data store of users, we will probably map it to some user identifier. If we cannot do it, this is also potentially important information for us, so we will mark it somehow. Device metadata to support the requirement of known devices, location metadata, and examples of network metadata, IP, internet service providers, etc. Now let's jump to some design ideas. First of all, we may start with designing our architecture based on some data stores, data warehouses. And just a short note here, I know that I'm just only touching tip of an iceberg here, and we could spend hours discussing solutions based on some data stores, and we would probably get it right, because this is possible. Databases are very specialized these days, and we could do almost anything with them. So, but I would like just to highlight some potential concerns that you should take into consideration before going this way. regardless of your engine of your data store and the schema that you have, regardless that whether you store events as raw events or some formalized or some formatted representation of them, you have this problem. You will need to query large, continuously growing set of data. And it's not impossible, but it may be difficult to get this right at scale of thousands requests a second and still be able to calculate your results in real time. So this is quite difficult. You can apply different techniques, but querying live information is quite complex thing. Then probably you would switch to have some materialized views, and this is quite good idea because you would like to avoid joins, because joins are quite expensive in data stores most often. So you would like to have some materialized views, and this is a way of storing information, storing some derived information aggregated out of as an artifact out of processing raw events. So you are not storing raw events anymore, you are just storing the derivatives. And you may find it nicely optimized for reads because you can create views for particular like screens in your applications, but it can be limiting in some way. One of these limits is that if you get rid of source events, you have no chance to do data reprocessing. So if you happen to find a bug in your computation logic, if you want to switch configuration, for example, analyze the data in 1 hour batches instead of 1 day, this is something that you cannot do with historical data because you just don't have it. So this is one of these potential limitations here. You can combine these two together. Probably you would apply some caching at some point, but when you apply caching, this is the point where actually you have one of the 3 most difficult challenges in IT industry, which is cache invalidation. So different type of problems. And if you look from the top on this idea, it's like your application is polling for results, is querying some data store in order to get the results instead of calculating them. So this is like a poll model. We will see shortly how to invert it. Our next idea may be Lambda architecture. And this was quite a thing a few years ago. But this is quite huge oversimplification, but still worth mentioning. So we have speed and the batch layer, and speed layer is all about providing the results quickly, as quick as possible, but you need to acknowledge the fact that these data, the results, will be just approximates, they won't be exact. Whereas the batch layer is something that can calculate precise results, exact results. So here, as batch layer is something that is running from time to time, probably with some time interval, you need to acknowledge the fact that this is coming with cost of additional latency. So you have this trade-off, and you need to make a decision, which is not that easy at some point. In batch layer, you also need to decide how you are chunking your data, and sometimes these chunks can be based on time, sometimes they can be based on amount of records, and maybe some hybrid of these, but still you need to apply some chunking, which may be in natural when you are processing the data as it happens. You also have 2 separate code bases to maintain, because these 2 layers most probably are different applications, probably they use different technology stack, and when it happens that you need to enrich the platform, invent or implement another feature, you need to enrich them both, so the cost is almost double. Here is where stream processing arises. If I were to summarize it in one sentence, it would be that stream processing is all about making sense of unbounded streams of immutable events. Two keywords here. Unbounded, because as soon as you start processing the data, processing your login events that we established, they will just never finish. The point when they can finish is when you close the business. So this is unbounded stream. And immutable, because events are all about the past. And unfortunately, past cannot be changed. We have no time machine, so yeah, what happened is noted, is stored as an event, but this never changes. Stream processing, which is also called as Kappa architecture, has other characteristics like events are processed as they happen one by one, in a way that every event matters. Every event triggers different calculations. You can have multiple derivatives out of even the single event, which we'll demonstrate in a second, and you have this nice continuity of the stream. You can introduce some ordering if you need it, but for some cases you can process them in parallel. So, and you don't need to introduce these artificial barriers like chunks of the data, because when you are chunking the data, you need to think what happens if interesting data happens to be in two different chunks. So this is a problem with batch processing. Here you have data as it goes and you process it as it appears in the stream. You have this nice stack unification because this is one platform, and you are moving towards event-driven architecture. So event, when it happens, it's just a trigger for different stream processors that are doing the job of calculating results for you, and event is just a trigger for them to do it, to calculate something and emit further events that will be probably processed by some downstream processors. Okay, examples that we will see are based on Kafka streams, and this is the platform of our choice. There are multiple great tools out there in stream processing world, like Flink, Storm, Spark Streaming, Samza. But what is quite unique about Kafka streams is that it's just a library. It doesn't need any special processing cluster, so you can just attach it to your JVM base, to any language, any application that is based on JVM language, and there you go. You can start using stream processing. Of course, you need Kafka as your underlying messaging bus, but this is what we already had. And yeah, this has some serious implications because you can deploy these applications in any platform of your choice. So you can use the same pipelines as you use, for example, for your web applications. Let's now define an input in a bit different way. So we have a message that is a login attempt, and here is the schema for it. We have a key of the message, which is session identifier, and I have structurized the event into two sections: event-specific data and metadata about the attempt. Now, what we can do in terms of the big picture. So we are consuming login attempts. This is our entry point. And our first stream processor that we are going to discuss is device recognition. So device recognition stream processor consumes login attempts, does its magic, which we will see how to implement in a second, and emits event if it happens to be, if the attempt is matching all these requirements, to be discovered as new device attempt. What is more, we have another stream processor that consumes the very same stream, like location recognition, and it discovers logins that are coming from new locations in context of particular user. These two streams then can be combined by yet another stream processor, which I called user notifier, and user notifier can use some knowledge like contact preference to send communications out to the user. these contact preferences can also be stored in Kafka, but it's a bit different story. So we have this nice topology here, but location recognition doesn't only need to do that. It can do a bit more. So it can also analyze some malicious location changes. So most often people cannot teleport themselves. If you know how to do it, just let me know. I would like to learn it. But normally it's not the case. So location recognition could discover such teleport commuters. I know that there are valid cases like VPN users, Tor network users that change their location from request to request, but this is something that we would probably be interested in, and we can have some specific business rules to analyze the traffic and to maybe limit some functionalities, maybe, yeah, different things. But the crucial thing about this is that we will know it. Later on, we will have a stream processor that analyzes traffic in context of coming from botnet or not. And if we see that, for example, IP is matching one of these IPs that we have on our blacklists provided by SecOps team, or we have our own intelligence to calculate IP reputation, we can report it as botnet attempt. And our last stream processor in this group, session statistics calculator, may get all these events as they happen, calculate like total attempts within given session, calculate total count of failed attempts within given session, maybe failure ratio, whatever we find useful for further analysis. These all streams can be later on combined in yet another stream processor that can, for example, be called malicious session analyzer, which will gather all streams together and have some like business logic that will discover malicious attempts. So we will know that something is coming from new location and it's probably botnet IP, so we can emit this event to malicious attempts that can be further on consumed by some, for example, authentication provider that can terminate the session, can redirect them to some honeypot or whatever. But the key thing here is that we have all the means to react on such situation. Cool. So this is like the big picture. Now let's deep dive into a specific implementation of one of these stream processors. I have chosen device recognition, and these are our outputs. These are the outputs that we will have at the end of our pipeline. So new device attempt, which is just a bit restructured input event. It has a key of session identifier. It contains user ID result and device metadata with addition of the hash that we will calculate in the process of stream processing in our pipeline. We also have known devices aggregate, which is keyed by user ID, and it just contains collection of devices used by a particular user. So we are again starting from login attempts, and the first thing we need to do is to convert our message a bit, and we are using map operator in order to do it. So map operator is converting one form of the object to another, and it's lifting and shifting few properties. As you can see, we have just set a new key for this attempt from device, which it's temporary name for this kind of event. And we have also calculated hash out of these properties that we think they will never change for given device. So for example, browser version can be changed with the updates, but as we would like to discover new devices, we need to decide on some fields that we will look into, and these fields will be used to calculate the hash. So these are just example fields that can be used. So now our event is mapped. We have it in more appropriate way, shape, and what we are doing first. So here we have two things to do. First, we need to build an aggregate with known devices. This is our idea. And the other thing is to detect whether this particular attempt, incoming attempt, is coming from the new device. So we are focusing on building this pipeline for known devices first. And known devices in our context will mean that device that is coming from successful login attempt. So this is where filter operator comes handy, and we are just checking the result. Later on, we are grouping these events by key, which is at the moment user identifier, and we are aggregating these events. Aggregate operator is stateful operator that consumes previous version of an aggregate and current event. So let's imagine a situation that user is coming with his first login attempt from a new device. An aggregate obviously will be non-existent, it will be empty. So we will just append this new device to an aggregate, to the collection of user devices. With the following attempts coming from new devices, we will just append the new device to existent aggregate. So this is this operator. And the result of the aggregation will be put in known devices stream. Job done. We have done the known devices aggregation. Now what we can focus on is discovering whether this particular attempt is coming from a new device or not. So the topology above will start from join operator. Join will be just a lookup whether this particular attempt from device has device that is already known or not. We will do it by key of user ID. And what is that we are joining towards? This is known devices table. So the table is what we create out of the stream. How does it work? So in stream processing frameworks, you have these two abstractions. One is a stream, that is when you are consuming a stream, you are interested only in independent events as they happen. You are not making any reasoning about their, you are not grouping them, for example. But when you say that I want to consume the data as a table, what you are really saying is that you are interested in the most recent version of given aggregate for particular key. So here you have independent events as they happen, as you emit them from the topology, but here you have a guarantee that you have only one event, only one message with the most recent version coming from the stream in scope of particular key. And there's this nice duality because you can always convert from a stream to the table, because stream is like a changelog and table is just realization of this changelog. And you can always go the other way around, so you can convert table to a stream by reading events. Okay, so at this moment we can ask ourselves the question, we have just received an aggregate for given user. We can ask ourselves the question whether the particular device and this hash that we calculated in the step before is present in an aggregate or not. If it is, we can, or the aggregate, if it is present, we are sure that this device is known. So we are enriching our attempts from device object with is known marker, and we put true as a value. But whereas if aggregate is not present for given user, it means that there were no devices by that time, or the hash is not existent in the collection, we know that this is no unknown device. Later on, we need to filter out all known devices because we are interested only in these that are coming from these attempts that are coming from new devices. Then we switch the key for the purpose of further processing in this malicious session analyzer, and we output it to new device attempts. So now we have two topologies. Here you may ask me a question, hold on a second, haven't you just told us that joins are a bit ineffective? how is that different then from databases, data stores? So, well, it is a bit different because of co-partitioning. So this is something that is guaranteed by Kafka and Kafka streams, but there are concepts like this in other stream processing frameworks as well. How it works? So to understand it, first let's see how the message is published to the topic in Kafka. When the message is published, Kafka producer gets the key of the message, which in this case is user X, calculates the hash, which is translated to partition number that will store this given event. So let's imagine our topic is divided into 3 partitions, and user X will always, because this is a guarantee of this algorithm, that is hashing algorithm, that it will always return same value for given input. So user X and events for user X will always be put in the partition 2 of this topic. Okay, and this partition will be assigned to one of our processing instances. When these processing instances are being started, they get assigned some partitions. And only one partition can be processed, the partition can be processed by only one processing instance. So we have yet another guarantee that corresponding partitions from copartition topics, and copartition topics are, if topics are copartitioned, then we mean that they have the same number of partitions, and in this case it's also 3. So corresponding partitions are consumed by the same processing instance. So what it implies is that when a message is put in the other topic, for user X, the same algorithm is used, the same number of partitions is there on the known devices topic, for example. We put it on partition 2, which then is consumed by the same processing instance. So we have just achieved this nice feature of data locality. We put an aggregate here, and when subsequent message is coming to the topic on the left, it will also flow into instance of DEF. And when we are about to do the join to see whether the aggregate is there, it's just a matter of in-memory lookup, because Kafka Streams is using RocksDB, which stores this data in native memory, but you can also use your own implementation, which is, for example, storing these aggregates in a hash map. So you have the data locality, which is key thing when you want to reason about highly performant systems and platforms. Okay, there is one flaw in this design. Can you name it? So we have a bit of race condition here, because in unhappy scenario, this flow may finish first. If this above topology is somewhat sluggish, lagging, or even down for some time, it needs to catch up. So if this, and this may be, two separate applications, depending on how you organize it. But if that's the case, and this pipeline finishes first, and your knowledge base of known devices is updated, then you may find yourself in a situation when you actually process the attempt, the device from this attempt is already added to known devices table. So it means that the result of the join will be incorrect. As we have no dependency, and this is distributed system, this situation can happen, and we need to protect ourselves from it. How to do it? So the above topology stays the same, but we need to introduce some sort of dependency. So in order to do it, we need to start our known devices topology from new device attempts. This is what we do here. So we have all the means to do it because we have result here. So we can do filtering of new device attempts. Then we can group these attempts by user identifier, aggregate them again, as we did in previous topology, and output event to known devices. And when you think about it, this is how it actually should work, because first we should discover something as coming from a new device, and only then add this device as known one. So this is like a logical flow, and it is represented now here. But yeah?
This known devices table is like an in-memory cache you are storing, or are you reading?
So this is in memory, yes.
Alright, so every time you are like starting the job like from scratch,
yes, you are reading this, yes.
Okay.
But I think it's possible to persist there.
Obviously, yeah, you can implement your own way of storing this, so you can put it somewhere in any database cache, whatever. This device, this topology and this architecture has also one small flaw that maybe not be visible in the case of new or known devices, but it will get visible if we are, for example, reasoning about locations. So this may be a bit abstract, but let's imagine a user that has thousands of devices, and he or she wants to log in from these devices. So what happens now is that our aggregates will grow quite large, and the device object can be quite large itself. It can contain multiple properties, so the aggregate will grow in size. What will happen here is that, as this will be quite unusual case, you will have an effect of data skew. So some aggregates, some events will be significantly larger than the majority of them, and these cases are really difficult to observe to fix and to observe in live environment. So how we can deal with that? How to fix it? We will use an idea of composite key, and no one ever said that in Kafka we should always use single valued string as our key. We can use a key that contains multiple properties, and the idea here is to use user identifier and device hash. So probably on production use case you would like it to be an object that has schema, probably stored in schema registry in Avro format, and that's fine because in Kafka, Kafka stores events, keys and values as bytes, so it doesn't really matter for it. It's just a cost of serialization, deserialization, which is ignorable, which can be ignored in this case. And yeah, this will be an object, everything will be fine. For the purpose of this example exercise, we will just use string, because we can also imagine a string that has concatenated values of user ID and device hash with some special delimiter. So, how the topology will change then? Actually, this is what changes. So our first map operator will do everything as it did before, but calculate different key. So the key now will be this composite key of user ID and device hash. We will use the same key, obviously, for doing the join. And current structure of our table looks like this. So we no longer have one input in this table, one row for particular user with an aggregate of devices, but what we have now is multiple rows for one user containing, so each row contains one device. This is the structure of the table we have now. In order to achieve it, when we filter, after filtering new device attempts, we need to map these attempts to have a key of user ID and device hash, obviously, and we put, for example, device as a value, but we don't really care about the other properties rather than the hash at the moment. but maybe it will be used for some for email purposes or something like this. So at the join time, when we are able to join anything from the table, so if we get non-empty result, at this moment we know that this device is already known because it was present in the table. Although when we get an empty result of our join, it means that the device, this particular hash is not known, so we mark this attempt as coming from the new device. And the rest of topology stays the same. And here we have optimized the topology by removing stateful operators that we had here. Grouping and aggregating is stateful. So this kind of optimization is very nice because we have reduced memory footprint because these stores are smaller, and we have saved some bandwidth because smaller events are sent over the network. Okay, some side notes here. Please define your goals clearly because it helps with defining your schemas and outputs, and it's much easier to actually enrich the schema later rather than strip it out from unused properties. Read the documentation and check defaults, because if you don't, it can hurt, and it happened to us. Consider delayed events, because this is a distributed system. Your client or application sending these events may be lagging, and events may come with some delay. So you need to know what to do about them. You should always, probably in some statistics use cases like the statistics calculator, you would probably need some time windowing, which is very concept topic, and I hope we'll meet here next year to discuss specifics of that, because it definitely needs its own session. And you need to consider delivery semantics. So Kafka and Kafka streams gives you all possible delivery semantics that you can imagine, at least once, at most once, exactly once. So choose wisely what you really need for your use case. Heading to the summary, if your platform has high throughput and you expect low latency, you have multiple inputs that may cause, where even one input may cause different calculation, you expect different results, you have multiple derivatives, and thus multiple outputs, you should probably consider stream processing. This will give you high scalability and great extensibility, because you can easily imagine building new stream processor with Kafka streams or KSQL, which is new fancy way of building stream processors that you run in somewhat called dry run, where you just don't attach results of this analysis to your live pipeline, which impacts end user, but you can just observe, visualize your results, correct your assumptions, and only then attach it to the end production pipeline. You have all the fault tolerance and data durability, because you are using features that Kafka has, like replication, etc. It's really good in these topics. You have data replays that we discussed before, so you can rewind time and you can replay events from the past and use your new processing logic. And one final note here, please keep big picture perspective, because this is really important. And when you have this big picture perspective, you can optimize the flow and work with this programming paradigm more effectively. That's it. Thank you very much for your attention. Now here are my contact details, and if you happen to have any questions, I would love to answer them.
Yeah, you mentioned at the very beginning that the streams are supposed to have the pretty constant size of the event.
This is most optimal if you can avoid this data skew. if you have, pretty much similar size of your events. This is where you can, if you have this situation, you can optimize particular parts of this pipeline more effectively, but this is not always the case.
Yeah, well, we try to use Kafka for ingesting completely different data from different sources, and I think this was the reason, one of the reasons that we thought this is not for us. So is there a point in using it if you know the events will be completely random?
Depends on this randomness, I guess.
Like, I guess you could partition by source, but still that's not.
Yes, you can do it, but yeah, you can apply a different compaction, different retention policy, maybe you can optimize different stream processors accordingly. So apply different batching, because Kafka also supports batching. You can batch few requests together and send them to and consume from the broker. So
okay.
yeah, maybe this way.
But okay, maybe this is out of the scope of this. But can the event size you define it somewhere, right?
You can change maximum event size. What?
Can it be dynamic?
Maximum event size?
Yeah.
Shouldn't be.
Okay.
Should be. So in very rare use cases, you should go over this 1 meg per message. This is not recommended, definitely.
Yeah.
You will have. We reached this point when we are doing this aggregates that had multiple devices, and when we extended this maximum size of the message, it impacted cluster stability.
Sounds like this is not the tool for the job then.
If you have huge aggregates, probably you can consider something else, or dividing them somehow.
Okay.
Okay, I have two questions. First one would be about the production numbers, because I'm really interested how many different unique user IDs do you have in production? That's the first one. And the second, how many partitions are on your topics?
So I'm not sure if I can share how many customers do we have.
Rough number, like more like 1 million or more like 10,000?
Millions.
So second and number.
We have.
Yeah.
So in our Kafka cluster, this is what I can share, is that daily we have we are producing 90 million of new messages.
On input, right? You're digesting.
Yeah.
Okay. So the second question I have is about because you showed only DSL API operators like stateful aggregates and so on, and I'm considering if you have tackled any problem that you had to implement something in processor API to solve it.
Yes, processor API is like different way to write your Kafka Streams applications. You don't use the DSL, but you are going under this abstraction of the DSL, and this is where you can do even more. You can achieve even more. We didn't have such use case. We have only experimented with that, but it's not running on production. But there are successful use cases which are described on Confluent blog, which I absolutely recommend reading, because there are very valuable blogs that you can read, blog posts that you can read, and describing different use cases, including processor API.
Okay, thank you.
Talking about latency, what's the average latency in this architecture? Like talking about devices. So it's like 100 milliseconds, so especially this join operation.
So going under 100 milliseconds is possible, but it depends on how much you care about it. So it is yeah, it's around 100 milliseconds you can expect these results, or hundreds milliseconds if you're processing, because it also depends on the processing logic that you have, how complex is it to calculate the hash, etc., and how big your objects are. But yeah, you can achieve this sort of results. Going under is possible, but yet it is more expensive.
We are talking about all the pipeline, parsing,
Input to output. Input, yes. Input to output. End to end.
And the second question regarding topics, what's the reasonable size of the topics? What can we can we get the maximum a couple of gigabytes, or it should be terabytes, or just should fit into the memory?
So, as far as I'm concerned, there is no limit for that. So if your cluster can support such big topic, it's fine. Although, yeah, and you can configure different retention policy. You can potentially keep events indefinitely, but maybe it's not something that you would like to do if you are really interested in latency. So you should probably have some different, output something after some time that you are no longer interested in some data, to some data warehouse, Hadoop for example, and keep what you really use for analysis, because yeah, it may have some impact, but yeah, you would need to benchmark it probably, how it behaves, because we have not reached that scale yet.
Probably to keep the hot data in this architecture, and then
Yeah, the data that you use for the pipeline, for sure. So some of this data you will keep indefinitely, like these aggregates, but maybe your input events may disappear from the cluster after some time. Of course, yeah, the Kafka scales that way that the amount of data is not impacting the performance of it if you scale, add additional brokers, etc. But yeah, you will need to, I cannot give you like exact numbers now.
Speaking of it, Kafka does have some kind of mechanism of controlling RAM usage. Like it wants ingest indefinitely, even though it can't process something out of the topic. It sees that ingestion is faster than processing and slows down on ingesting.
So processing and ingesting are two totally separate processes.
Well, yeah, but you process something, and then once you're done with it, you can throw it away, so you don't use RAM.
Yes. So as we mentioned before, you can implement your own mechanism to handle this data in RAM. Mm-hmm. But yeah, the stateful operators, they will need to keep this data.
You don't want to throw that away, but the events themselves, will the topic grow indefinitely?
Potentially it can.
Okay.
But the topic is not stored in the RAM.
Yeah, topic is stored on disk, on broker.
Yeah, and that's why you have retention policy, because the old events are dropped. We don't have to do it, but yeah, so it's risky to have infinite retention policy. I
Yes
have
and
one
no.
more question
Yeah.
about the join, because you showed the join with the two topics and they were partitioned in exactly the same way.
It was the join between stream and the table. Yeah.
Okay, but you can also join
Two streams. Yes.
And is it necessary to have them partitioned in the same way, or Kafka streams will do some shuffling for us?
No. In order to join some topics to some stream to a table, stream to stream, table to table, you need to have them co-partitioned.
All right.
So you need to have same number of partitions on both. This is the prerequisite. Otherwise, Kafka streams will just throw an exception.
Okay, but group by will do repartition.
What you can do, if your input topics happen to have different partition layout, different partition size, amount. Let's say one topic has 3 and the other one has 6. You can do it like the way that you have this. You consume this topic that has 3 partitions. You use to operator or through operator that outputs these events to another topic that has like very quick retention timeout, retention policy, and so you like add additional step to match the partition counts. So from 3 you achieve 6, and this is where you can join together. Or you can downscale from 6 to 3, depending on your need.
Yeah, so the question was about stream versus stream joining, and this is quite tricky in Kafka streams because you cannot like join stream with another stream just like that. You need to specify also time windows for the stream. This is very different from the stream versus table joining.
Yes.
Okay.
This is the topic that I highlighted only here, this time windowing and actually playing with time in Kafka streams. This is the topic common to all stream processing platforms. So, and this is quite broad, but I hope we'll have another session about this. Okay, thank you very much. It was a pleasure.